Alright, let's talk briefly about quantum mechanics. I don't want to make this too long of a video because quantum mechanics is the most confusing subject in all of physics. Even Richard Feynman said, if you think you understand quantum mechanics, you know nothing about quantum mechanics, and he won the Nobel Prize in quantum electrodynamics in 1965 for his discoveries in that field. When we think about quantum mechanics, we should think about these subatomic particles, like electrons or photons or mesons, whatever you want, existing as waves in space. So if they exist as a wave in space, they're not a particle, it's a wave, and there's a certain probability of finding the electron along that wave. And it's a wave, it's an actual wave that covers three-dimensional space. There's a certain probability of finding the electron within that space. And a lot of physicists at the time, when these things were being discovered in the early 1900s, they had big problems, early to mid 1900s. They had big problems with there being a statistical aspect to physics, because up until that point, nothing ever required a certain probability of being true. It was just either true or not. It was either falsifiable or not. And this is falsifiable too. There's just some statistical tricks that come about through studying these things. So we think about the wave function, right? This is big. This is Schrodinger. This is, Feynman. This is Dirac, the wave function. So there's a wave in space, right? The electron is that wave, quite literally. It's not a little ball. The electron is a wave. Okay. If we try to pinpoint the position of that electron and take a measurement, what a measurement means, or some people say an observation, that's not really a good term for it, because what you mean is you bump something into it, like a photon, to observe it, right? Some optical device that can measure this thing. When you bump into it and its position is certain, its momentum becomes uncertain. You don't know what its momentum is. It's not that it could be anything, it just could be a range of values. Once you pinpoint the position, the momentum varies by 1/2 h cross. It's a constant. It's a variation of Planck's constant. And then, conversely, right, if you measure the velocity or the momentum of this particle, then its position becomes uncertain. So you can't know, in quantum mechanics, in reality, you cannot know the position and the momentum of a particle at one point in time. And so that's a big thing. That's called Heisenberg's uncertainty principle. Werner Heisenberg was this Nazi who discovered a lot of great stuff in physics. Not a great guy. Tried to help the Nazis build the bomb unsuccessfully. What's up? Quantum mechanics is, again, the most confusing subject in physics by far. It's very confusing, but it's very rewarding when you start to understand and explore the things that it has to offer and the predictions that it can make. So, the big takeaways here are, quantum mechanics means particles exist as waves, not as particles. And when you pinpoint the position, the momentum becomes uncertain, or if you pinpoint the momentum, the position becomes uncertain. That's what quantum mechanics means in terms of the underlying principles that make it all work. So everything kind of falls out of those principles. What kind of implications does that have? It means a particle can jump out of a well where it otherwise couldn't, classically, right? If something exists in a well, I'll put up a picture of what they call, sometimes there's a finite square well, infinite square well, whatever it might be. If it exists as a wave and the waveform travels above the well on the other side, but inside the well is the bottom of the wave, that means that most likely the particle won't be able to jump out of the well, but sometimes the particle will be able to jump out of the well. And when you scale that up, it can become a very impressive new way to develop things like anything that has to do with work and energy transfer, engines, for example. You can overcome the chute, what's called the chute of a motor, by using principles of quantum mechanics to get something to be in a place where it couldn't otherwise be classically. That means you can create motion out of just using these principles. So very cool stuff. Quantum mechanics is very interesting. It's very hard, but it's very necessary.